Hey, Algebra 2 Honor students. Today is Unit 12, Day 6. We are on page 35 of the packet, and we are looking at some exponential applications revisited. So back in Unit 11, we talked about some really important formulas to talk about things that grow exponentially or decrease over time at an exponential rate. So if you remember those formulas, fill them in on the blanks. I figured I'd give you a quick chance to see if you remember them first. If you're going to hit pause, once you unpause, you will see me start filling these in for you. So here we go. The three formulas are the following. Something of the form A equals P times 1 plus or minus R to the T. This is just kind of for general growth and decay based on an annual rate. Okay, so we have that plus or minus in there if we're increasing over time or decreasing. All right, then in the middle we have A equals P times 1 plus R over N to the NT power. Notice how I just have a plus here, not a plus or minus, and it's because these are typically used for bank accounts where money is growing, okay? So look for the keyword compounded if you're gonna use this formula. If interest is compounded monthly, quarterly, semi-annually, that's what that value of N represents, okay? So if interest is compounded a certain number of times within a year, then you're gonna use this formula, okay? And then finally, we have our final formula of PERT. And the keyword that you're gonna look for with PERT, of course, is if something is happening continuously, okay? So if you made mistakes with that on the last test that you didn't recognize, okay, it said increasing continuously or decreasing continuously, then make sure you pay attention in this unit that if it ever uses this word, we've gotta jump to PERT. Okay, these applications are really the same exact types of questions that we did in Unit 11. The only difference is that now we have an algebraic way to solve some of our situations where we're looking for time. You know, if we don't know how much time it takes for the end amount to grow or decay, then we can figure out, based on what we know about logs, how to solve algebraically for time. So we'll see that. All right, here's the first example. In 2005, the population of a city was 43,600 people. Suppose that the population increased at a rate of 2% per year. So we are increasing. I don't see anything about continuously. I don't see anything about compounded. So we're definitely going to go to our original formula here and determine the population in 2010 and then 2015. So if the original year is 2005, 2010 is when time equals 5, and then 2015 is when time equals 10. So the model for part A for 2010 would be the amount of people is the initial 43,600 times 1 plus 0.02 to the fifth power. So that's going to be 2015. And then for 2015, same idea. And by the way, you could, of course, make that 1.02 if you like. All right, so we'll do that to the 10th power. Let's see what we get for those populations. Doesn't say right around, but remember, population, it definitely makes sense to go to the whole number here. So 43,600 times 1.02 to the fifth. That's this amount, 48,000, we'll say 138 people approximately. And then for the next one, you could actually just go back and copy paste and then change your exponent to a 10 up there. And that's 53,148 people. Okay, so we have those two amounts. That's a pretty easy, quick plug-in. Then it says part B, according to the model, when will the population reach 60,000? So that question of when means I'm solving for the time when I know that the end amount is 60,000. So part B, 60,000 would equal 43,600 times 1.02 to the T. Now, in the last unit, Unit 11, we would have stopped right away and done Y1, Y2. And just keep in mind the expectation in Unit 12 is that we don't do Y1, Y2. You can use that as a check method, but we're just going to solve this algebraically. We have the skills to do that at this point. So the very first step, if you want to algebraically solve this equation, is divide both sides by 43,600. So when I do that, I'll try and see if I can just have the calculator quickly reduce that fraction, 60,000 over 43,600. It's this decimal, but math frac, it's 150 over 109. All right, so 150 over 109 equals 1.02 to the T. So think back to day 4 in this unit when we solved exponential equations. Once you got the exponential base by itself, then you can introduce a log. And what log am I going to take of both sides? I'm going to choose the base of the log to match the base of this exponential. So in the next step, I'm going to write log base 1.02 of that fraction, 150 over 109, equals log base 1.02 of 1.02 to the t. That looks weird. We haven't done a lot with log bases that have decimals in them, but that's an okay and a legal step. Because if I choose the base of the log and the base of the exponential to match, then on the right side, you just get t. And on the left side, whatever log base 1.02 of 150 over 109 is, that's how much time it takes. Now, it didn't say what around, but if I told you it took this much time, it wouldn't mean much to us. So let's type it into the calculator. I am going to use log base here. You can use change of base if you really want to, but math, scroll up to option A. You can type in, of course, whatever base you want there. And then I'll do a fancy fraction for 150 over 109. All right, and all that being said, we get that it's about 16.1 years, okay, for that to happen. So again, we can confirm this graphically with y1, y2, but the expectation moving forward is that now we have some good algebraic skills with logs to be able to solve these situations. Okay. All right, moving on to number 2. Alex is purchasing a new car for $30,000, which depreciates. Okay, hopefully even if you've never really heard of that term, you think of depreciating as going down. It's decreasing at a rate of 15.5% each year. According to the model, will the car ever have a value of $0? All right, so the original model would be that the amount that the car is worth is $30,000 times 1 minus 0.155 to the t. Okay, it's decreasing at that rate. I don't see compounded. I don't see continuously. So make sure you just use that original model again. And 1 minus 0.155, if you want to clean that up, is 0.845. So what I want to know is, will the car ever reach an amount of $0? I mean, maybe to some people it would, but mathematically, is it ever going to be worth nothing? Well, if you divide both sides by 30,000, you still get 0 over here. So we have 0 equals 0.845 to the t. And I want you to think about this logically here. If I do a number to a power, will it ever output an answer of 0? I mean, think about what the graph of this would look like too. If you have an exponential model, think about where we have some asymptotes, and this is actually decreasing, right? So it would be exponential decay. Well, the answer is, no, this is impossible. There's no input for t that would output a 0 here, okay? So because this has no solution, the car's value in theory will never actually reach 0. Okay? But we can figure out part B. According to the model, when will the car's value be half of its original amount? So for part B, I'm going to have you guys try it. See if you can do part B on your own. We will go over it next time we are in class together. All right, moving on to the next page. In example 3, we have Grandma. What's Grandma doing? Wow, Grandma's really nice. Grandma has $20,000 to invest and wants to save $32,000 to help her favorite grandson purchase a new house. How nice, Grandma. She expects her investment to earn an average of 6% a year, compounded quarterly. There's a keyword we got to pay attention to. In how many years to the nearest year will she reach her goal? Well, when you have anything that's compounded a certain number of times, you're going to use the formula, the 1 plus r over n to the nt. Okay, hopefully that you jumped right to that. All right, let's plug in what we know. We know that the initial investment's $20,000. Thank you, Grandma. Then we want to save, and we want the end amount to be $32,000. So that's going to go for capital A. Times 1 plus the rate. The rate is 6%, so 0.06 is up here. Compounded quarterly, so that's to over 4. The exponent would be the 4t power. Okay, so how many years, t to the nearest year, will she reach her goal? Okay. All right, so here we go. We're just going to start solving this pretty much identically to how we did number 1 on the front. You're going to divide by 20,000 first. get that to the other side. So if I divide the 20,000 over, let's see, 32 over 20 is what you'd be left with here, which reduces to 8/5. And the 1 plus 0.06 over 4, if you want to type that into the calculator, that's 1.015 to the 4t. All right, now that I have this cleaned up as nicely as I have it, the exponential base is by itself. So at this point, we are now ready to introduce a log on both sides. What log base am I going to choose? Choose the base to match that exponential base. Log base 1.015 of 8/5 would equal log base 1.015 of 1.015 to the 4t. And as soon as that exponential and log base match, on the right side, you just get 4t. And on the left side, I'll recopy log base 1.015 of 8/5. Okay. Last but not least, we want to get t alone. So if we divide both sides by 4, this is how many years it takes. So just go up to grandma and say, hey, grandma, in log base 1.015 of 8/5 over 4 years, you will have the money that you want. Well, grandma wants to know what that actually is in years. To the nearest year, it said. So let's do some good log base here. So math option A, log base 1.015 of 8/5. And then I have to take that and divide it by 4. And that should be good on the home screen, all like that. And we get 7.89 is how much time it takes. So therefore, to the nearest year, it's going to take grandma 8 years to help you save for a down payment on the house. Thank you, grandma. Okay. Last but not least, we'll finish up with example 4 here, and then we'll do more practice next time we're in class. This year, Eric deposits $3,000 into a new savings account that pays 5.8% annual interest, compounded continuously. Okay, there's my key word. All right, compounded continuously is definitely the PERT formula. How long will it take for his savings to double? So you're going to see this question come up a lot of how long, because now that we know logs, we can use logs to algebraically solve for that exponent of time, okay? Let's plug in what we know. This year, he deposits $3,000 into a new account, so that's the initial amount. E is just E, right? Remember, E is a number. It's about 2.718. The account pays 5.8% interest, so the rate of 0.058, that gets plugged in for R up in the exponent there. How long will it take? That means I don't know time for his savings to double. So I want the end amount on this side to be $6,000. Okay, this solve is going to look pretty much the same as the others, except we want to think very carefully about what I'm going to use to get rid of base E in a moment. Okay, you're still going to divide both sides by 3,000. 2 equals E to the 0.058t. Now here's kind of the key moment. If you have E as your exponential base, what log should I take of both sides to get rid of base E? Well, it would make sense to say log base E of both sides. But guess what? Remember, log base E is the same thing as ln. It's the natural logs. So whenever you have base E, I don't want to see this. You guys are good enough that you can write natural log of both sides. I'm going to take the ln of 2, and that would equal the ln of E to the 0.058t. Okay. So I know that this side is just ln of 2. Remember, if this is the same thing as log base E of E to the power is the power 0.058t. Okay, so last step, divide by 0.058, and we'll figure out how much time it takes for our money to double. All right, so remember, we have the ln key right next to the 4 over here, so ln of 2 divided by 0.058 is 11.95. So we'll go to the nearest year, just like we did up above. We'll say it's approximately 12 years for this to happen. Okay, so I like these questions. You know, it's definitely some good practice with solving some exponential equations using logs. I especially like the last one when it's compounded continuously. The log that we're going to choose on both sides here is the natural log. We will do more practice like this next time we're in class. If you have any questions, let me know.